Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on analytical dynamics or classical mechanics, chapter Lagrangian dynamics, lecture number 4, in which I will derive the Lagrange equations of motion of second kind. Now, we will derive the Lagrange equation of second kind. Let q1, q2, qn be n generalized coordinates of a dynamical system. R mu be the position vector of muth particle of mass m mu at any time t. So that R mu vector is the function of generalized coordinates q1, q2, qn t. This is number 1. Let F mu vector be the external applied force on the muth particle of mass m mu, and delta R mu be the virtual displacement of the muth particle. Therefore, total virtual work done by the external applied force F mu dot virtual displacement delta R mu vector, and total is sigma here mu, and total virtual work done by reverse effective force. Effective force is mass into acceleration m mu r mu double dot. This is mass and this is acceleration, second order derivative, dot virtual displacement. This is mass into acceleration. This is force and this is displacement. Force multiply displacement is the work done. This is virtual displacement. So this is virtual work done, and total virtual work done by the effective force is sigma here. Let this is number 2. This is number. Since by D'Alembert's principle, we know that total virtual work done by external applied force equal to total virtual work done by effective force, implies that sigma mu F mu dot delta R mu, this equal to sigma mu a mu r mu double dot, this is acceleration, dot delta R mu. This is number 3. Since R mu be the position vector which is the function of generalized coordinate q1, q2 qn t, from 1 we get delta R mu vector, this equal to partial derivative of R mu vector with respect to q1 coordinate delta q1 plus partial derivative of R mu vector with respect to second coordinate q2 delta q2 plus plus R mu vector, partial derivative of R mu vector with respect to qn delta qn. We are not taking partial derivative of R mu with respect to t and delta t because it is virtual displacement. Since for virtual displacement delta t equal to 0 implies that delta r mu vector equal to here 1 1 2 2 n. So we may write this in sigma form. Sigma I equal to 1 to n partial derivative of r mu with respect to qi delta qi. This is number 4. Using 4 into we get sigma mu f mu vector dot delta r mu vector. This will be equal to sigma mu f mu vector dot sigma I equal to 1 to n partial derivative of r mu with respect to qi delta qi, and this will be equal to sigma I equal to 1 to n. We may take this outside, and here we take mu sigma mu f mu vector dot partial derivative of r mu with respect to qi delta qi. This is number 5. This equal to sigma I 1 to n. Let this is denoted by qi delta qi. Let this is number 5, where qi equal to sigma mu f mu vector dot partial derivative of r mu with respect to qi is called the generalized component of external applied force. Let this is number 6. Now sigma mu a mu r mu double dot delta r mu equal to sigma mu a mu r mu double dot. We put the value of delta r mu taking from 4. This is sigma delta r mu partial derivative of r mu with respect to qi delta qi I equal to 1 to n, and this is double dot. This is equal to sigma I equal to 1 to n outside. We take here sigma mu a mu r mu double dot partial derivative of r mu vector with respect to qi delta qi implies that sigma mu a mu r mu double dot delta r mu equal to sigma I equal to 1 to n sigma mu a mu d by dt r mu dot partial derivative of r mu with respect to qi minus r dot d by dt partial derivative of r mu with respect to qi bracket closed, and ultimately this bracket also closed, delta qi. We may write sigma I equal to 1 to n bracket sigma mu a mu d by dt r mu dot partial derivative of r mu vector with respect to qi minus r dot, exchange the derivative operator, partial derivative with respect to qi d by dt r mu vector bracket closed delta qi. This equal to sigma I equal to 1 to n bracket sigma mu a mu bracket d by dt r mu vector dot partial derivative of r mu with respect to qi minus r mu vector dot, this is r mu dot partial derivative of with respect to qi, this is r mu dot d by dt r mu is r mu vector dot bracket closed delta qi. Let this is number 7. Let T be the kinetic energy of the dynamical system, then T equal to sigma mu half a mu mass into velocity square. Let this is number 8. Implies that partial derivative of t with respect to qi dot equal to sigma mu half a mu to r mu vector partial derivative of r mu dot with respect to qi dot, this equal to sigma mu a mu r mu dot vector partial derivative of r mu dot with respect to qi dot, this is number 9. Now partial derivative of t here with respect to qi equal to sigma mu half m mu to r mu dot partial derivative of r mu dot vector with respect to qi. This is sigma mu m mu r mu, this is dot, r mu dot partial derivative of r mu dot with respect to qi. This is number 10. Since r mu vector is the function of generalized coordinate q1, q2, qn and t, implies that dr mu by dt derivative with respect to t, this is equal to partial derivative of r mu with respect to q1 and dq1 by dt plus partial derivative of r mu with respect to q2 dq2 by dt plus partial derivative of r mu with respect to, let here qi dqi by dt plus plus partial derivative of r mu vector with respect to qn dqn by dt plus partial derivative of r mu vector with respect to t dt by dt. We may write this as r mu vector dot derivative with respect to t is dot equal to partial derivative of r mu vector with respect to q1, here dq1 by dt means q1 dot, here partial derivative of r mu vector with respect to q2, here q2 dot plus partial derivative of r mu vector with respect to qi dot plus partial derivative of r mu vector with respect to qn dot plus partial derivative of r mu vector with respect to t dt by dt is 1. Here we must have to write dot because here dot, so here dot, here dot, here dot, here dot, here dot, here dot, these are dot products. Taking partial derivative with respect to qi dot, partial derivative of r mu dot with respect to qi dot. Here we have q1 dot, here q2 dot, here qi dot. Derivative, partial derivative with respect to qi dot with respect to qi dot. Here 1, here 0, here 0 and other terms 0. Only remains here 1, here partial derivative of r mu vector with respect to qi. Partial derivative of r mu vector with respect to qi. Let this is number 11. Using 11 in 9 we get this place. Partial derivative of t with respect to qi dot equal to sigma mu a mu r mu dot, and this is partial derivative of r mu with respect to qi. Let this is number 12. From 7 we get left side sigma mu a mu r mu double dot dot delta r mu vector. Right side sigma I equal to 1 to n bracket d by dt sigma mu a mu r mu vector dot partial derivative of r mu vector with respect to qi minus sigma mu r mu vector a mu vector here dot r mu vector dot partial derivative of r mu vector here dot here qi partial derivative of r mu dot vector with respect to qi, and here delta qi. This equal to sigma I equal to 1 to n d by dt bracket sigma mu a mu r mu vector dot using 11 we get partial derivative of r mu dot with respect to qi dot minus sigma mu a mu r mu vector dot partial derivative of r mu dot with respect to qi here delta qi. This will be equal to sigma I equal to 1 to n this value from 9, and this is by 11 using 11 from 9 we get this value is partial derivative of d by dt firstly, then partial derivative of t with respect to qi dot minus here this value is partial derivative of t with respect to qi and delta qi using 9 and 10. Let this is number 13. Using 5 and 13 in 3 we get sigma I equal to 1 to n qi delta qi equal to sigma I equal to 1 to n d by dt, partial derivative of t with respect to qi dot minus partial derivative of t with respect to qi delta qi. This is number 14. Since all generalized coordinates qi's are independent, so we may equate the respective coefficients of both sides of 14. Therefore, d by dt, partial derivative of t with respect to qi dot minus partial derivative of t with respect to qi equal to capital QI. I equal to 1, 2, dot, 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 n. This is equation number 15. These are Lagrange's equations of motion of second kind for a holonomic system with n degrees of freedom. Now, case 1. When the system is wholly conservative, let the external applied force is conservative, then forces are derivable from the potential function. Let V be the potential function, and potential function is the function of position coordinates. Means here potential function be the function of generalized coordinates q1, q2, dot, 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 qn. Delta V equal to partial derivative of V with respect to q1 delta q1 plus partial derivative of V with respect to q2 delta q2 plus dot, 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 partial derivative of V with respect to qn delta qn, and this will be equal to sigma I equal to 1 to n partial derivative of V with respect to qi delta qi. This is number 16. Since virtual work done equal to delta w, and we know that this virtual work done equal to negative of change of potentials, and since virtual work done is sigma mu equal to 1 to n f mu dot delta r mu equal to sigma I equal to 1 to n qi delta qi, implies that minus delta V equal to sigma I equal to 1 to n qi delta qi, implies that this is minus sigma I equal to 1 to n partial derivative of V with respect to qi delta qi equal to sigma I equal to 1 to n qi delta qi, implies that qi equal to minus partial derivative of V with respect to qi. This is number 17. Using this value in 15, we get d by dt partial derivative of t with respect to qi dot minus partial derivative of t with respect to qi equal to minus partial derivative of v with respect to qi implies that d by dt partial derivative of t with respect to qi dot minus partial derivative of t with respect to qi plus partial derivative of v with respect to qi plus 0 equal to 0. Let this is number 18. Since partial derivative of v with respect to qi dot equal to 0, because since v is not function of qi dot. This is number 19. Therefore, equation 18 may be written as d by dt partial derivative with respect to qi dot t minus v. Here partial derivative of v with respect to qi dot is 0. Here it was only t. Here we have written t minus v minus partial derivative with respect to qi t minus v. Here t, here v is equal to 0. Let this is number 20. Let t minus v equal to L, which is known as Lagrangian function or kinetic potential of Lagrangian system. Therefore, equation 20 is written as d by dt partial derivative of L with respect to qi dot minus partial derivative of L with respect to qi equal to 0, I equal to 1 2 dot 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 n. This is Lagrange's equation of motion for a conservative system. We will deal the other cases in the next lecture. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.